Okay, hello everybody. My name is Claudia Cauli. I'm a PhD student at the University of Gothenburg, and the paper that I'm presenting now is titled Closed and Open World Reasoning in DL-Lite for Cloud Infrastructure Security. This is joint work with Magdalena Ortiz from TUVN and Neil Piterman, who is my advisor at the University of Gothenburg. So let me set some context first. So why are we trying to combine closed and open world reasoning for cloud infrastructure security? So in some previous work that we have published this summer at CAV as a case study, what we did was we used description logic to formalize and encode some special configuration files that are used in cloud deployments for specifying, essentially users use these files to declare all the resources that they want to deploy in their infrastructure in the cloud and how these resources are configured. So we've used description logics in this case study to model separately some central specification files that are given from the cloud provider and the actual configuration files the users write. And this fit actually quite well as respectively modeled in T-box axioms and A-box assertions in description logic in a fairly lightweight description logic such as DL-Lite. What we did later in the same case study is that we ran a set of configuration checks because the aim was to check compliance of these configuration files to a set of security properties. What we found when we were conducting the case study was that the description logics that we actually needed for best encoding this type of situation and for best checking this type of properties actually was slightly different. And that's what led to the work that I'm presenting today, because this paper essentially introduces two main contributions that solves these two different problems. We introduced what we call core closed knowledge bases. Core closed knowledge bases are lightweight, in our case right now, description logics, that in addition to a normal T-box and A-box, also have what we call the core of the system, which is a combination of a set S and a set M. So for example, what we see here in this little box, let's assume that we want to create an infrastructure. And in this infrastructure, we have mainly two pieces of storage. Now here they're called S3 bucket because the case study was based on the AWS cloud. And one type of storage, the AWS cloud, is called S3 bucket indeed. So let's say that we have a bucket that is called data, and data stores logs on another bucket that is called logs. But in addition to the concept of bucket, we also have a higher level concept of storage, which may not be a storage of the type S3 bucket. It may even be given by another cloud provider. And what's more important is that we do not own the storage, the external storage. There may be some additional type of resources that we are not declaring ourselves. We don't own the configuration file, and we have no knowledge on the configuration of these resources. While instead, what we want to achieve here is that the information that we're modeling and that it's part of the core is actually complete. We do actually have full information. So the desired interpretation here is that all the information that is missing, all the assertions that are missing from the core are to be interpreted as false. And this is what we achieve in the core closed knowledge base. The second problem that this paper tackles is a way to express properties that is more tailored to this security application. So what we found in the case study was that most of the properties that we were expressing actually fall into two types. So they were either some mitigation to security vulnerabilities that must be in place in the system, or they were exposure to security vulnerabilities that might be in the system. So since we were interested in contrasting these two types of informations that we can extract from the system, so things that are certainly there and things that might be there, so what we did is we introduced what we call here must and may queries. Now, must and may not be the best term ever, but we actually borrowed the terminology from model checking, three-valued model checking, that community. But what's important here to notice is that must and may queries are Boolean combination of conjunctive queries. They are nested inside some must or may operator. And this actually explains why most of the effort that we did in this paper was focused on conjunctive query satisfiability, because we used conjunctive query satisfiability to solve the main queries. Let's dive a bit deeper on what are actually formally these core closed knowledge bases. So, like, ultimately, the syntax of the concept, axioms, and assertions in core closed knowledge bases is the same as DL-Lite. What we found is that DL-Lite is more than enough to encode these configuration files. The difference, though, is that we have this core, as I mentioned earlier, this core with an S box and an M box. And what goes into the S box and what goes into the M box actually depends on the special partition that we have on the alphabets. Core closed knowledge bases are defined on sets of concepts, roles, and individuals that are partitioned into an open, more classical partition of predicates and individuals, and into a partition that is actually, let's call them partially closed predicates, because this is really the partially closed predicates really gives an idea of the difference that this type of closed-word reasoning has compared to most of the works that some people have done in the past with closed predicates. So the peculiarity of the work that we have here is that the predicates are not fully closed. The predicates are closed only when it comes to assertions that refer to individuals part of the model. In fact, the specific assertions that fall into the scope of an M-box are all the assertions that talk about individuals in the set of model nodes. So all of these A with subscript M that we see here in the bottom left in the assertions, referring to the partially closed predicates, so predicates with the superscript S. So this is what tells people who are trying to use core closed knowledge base to model their system what goes into an M-box and what doesn't. For example, so if we want to model the setting, the small toy example that I introduced earlier, one way that we can do that by using core closed knowledge bases is essentially by putting all the assertions that refer to the core part of the model, to our known, fully known configuration files, into an M-box. And this would allow us to achieve the final interpretation that we want to be given to this model, so that all the assertions and all the properties that are not specified inside the model are actually false. So yeah, the semantics, in fact, the semantics of core closed knowledge bases is a set of interpretations with the unique, with the characteristics that interpretations, in order to model a core closed knowledge base, they need to model M assertions, so assertions that normally fall into the scope of an M-box, if and only if the assertion is actually in the M-box. Very nicely, what we realize is that it takes very little modification to existing results that apply to DL-Lite knowledge bases to compute satisfiability. And satisfiability in core closed knowledge bases is fault reducible, as it is in normal DL-Lite knowledge bases. To achieve this result, then we simply need to adapt the notion of chase, and from the notion of chase, the notion of canonical interpretation. The difference here is that the chase is allowed to be built only starting from the boundaries of the assertions that are contained in them, but can never expand inside them. So there is no possibility of new inference being drawn inside the M assertions, because if the M assertions are not there, then the M assertions are false, essentially. Let me actually specify that all of this based on the assumption that M is completely consistent with respect to S. Moving on with the results, conjunctive query entailment and satisfiability. As well, similarly, conjunctive query entailment is AC0 in data complexity. This is similar to the results for normal conjunctive query entailments over the DL-Lite knowledge bases. Regarding conjunctive query satisfiability, we have a slightly different result. We have to resort to satisfiability of core closed knowledge bases by dropping the unique name assumption on the open part, which is the only part that was actually adopting the unique name assumption. So we have that conjunctive query satisfiability is log space in data complexity. Thank you. Finally, so the last contribution of the paper was introducing this master array query, which are Boolean combination of conjunctive queries in the scope of a master array. I think I mentioned earlier, but we solve the mask queries by resorting to certain answers, and we solve the make query by resorting to the satisfiability of answers of a query. So we rely on the results on conjunctive query entailment and conjunctive query satisfiability. And we conclude by saying that answering whether a tuple satisfies a must make queries over a core closed knowledge base is log space in data complexity again. Future work. We have been working on combining these core closed knowledge bases with some action or temporal reasoning formalism. This will be very important in the application that we're working on, because one of the things that users do on their configuration files is that they have permissions to perform certain actions. And some of these actions are not simply, for example, read or write actions. Don't change the infrastructure, but some of these actions are what we call mutating actions. Mutating actions actually change the configuration of the infrastructure. So for example, they can delete an existing node, introduce new nodes, or change the configuration of some nodes. And what we want to achieve by introducing even modeling and reasoning upon actions in this core closed knowledge base is we want to reason on the potential impact that updates and changes and modifications to the knowledge base would have on the compliance of the knowledge base to security properties. Some of other things that we think would be interesting to work on is, for example, whether conjunctive query satisfiability can be done in AC0 data complexity. Can we write a formula for that? Can we extend core closed knowledge bases for more expressive description logics? And can we maybe adopt some non-monotonic extensions to reason about access policy? These are all very relevant questions in the context of cloud deployments, infrastructure as code, and modeling and verifying compliance of cloud configurations in general. So this is all for this work, and please do reach out to me in case you have comments, ideas, or any questions in general. Thank you.